Hello everyone, the topic of our group is analysis of two action recognition methods with still images. And here is our table of contents. In this presentation, we will firstly introduce our topic and the related work. Next, we will demonstrate how we find and handle the dataset. Subsequently, the way how we implemented the recognition will be mentioned. Finally, we will analyze our result and conclude it.
Now we are going to tell about our introduction. Nowadays, because recognize human action is used in a lot of fields, such as medical to help people. Therefore, we are extremely interested in this topic. This is our motivation, and our goal is developing an AI system to detect human action. We choose two different methods to compare, and we want to improve them.
Now, let's discuss the part of related work. In Method 1, we refer to a paper titled Learning to Detect Human Object Interaction. In this paper, the author proposed the method of human object region-based convolutional neural network. And we use this method as our core concept. Try to use three different streams to achieve the goal of action recognition.
Now, the method 2 is learning to detect human-object interaction. This paper different from the typical recognized action it is detect static image, and it is difficult than video because video can give more information, and the paper it breaks down the action into a small segment. This paper use YOLO to detect its interesting part, and use AlexNext to classification. The difference between our work and existing one is we detect the image, not the video. The existing one usually detect video, and existing one is usually combine convolutional network and long short-term memory networks to extract the spatial temporal feature from the videos, and it usually with the 3D CNNs handling both spatial and temporal.
In our work, we use bCoco, verb in Coco as the dataset. It can be viewed as the subset of Coco, which collects only verbs. We follow the instruction and using Coco API to download image, and use the official annotation from Coco to get more information, such as bounding box. We implement this idea in croppedimage.py. Here, we download the image and crop into 4 pieces: agent, object, union, and intersection using the given bounding box. Additional, since the method in the paper only accepts one person and one object, we fill out some image here.
However, every coin has two sides. Although vCoco provides numerous and annotated pictures, it still exists some problems. First of all, the differences in the number of photos vary greatly across each category, which may contribute to devastating results that makes machine to recognize all the actions as the same one. Secondly, the quantity of testing data is significantly greater than that of training data. It leads to a severe shortage of our training data. In order to solve these problems, we have done some improvement. At the beginning, we delete the action whose picture numbers are less than 400. Next, select the equal numbers of each action's pictures. Finally, split the training and testing dataset on our own.
And our usage of the split dataset is like the code. And at first, we ignoring the action fewer than 400 images, and we split the data with the test side 10% and train side 80%. And every action, we actually select 400 pictures. And this 400 picture is ordered by the number of labels.
Our baseline model is just a simple multinomial logistic regression. Logistic regression is a common method for binary classification. Since we have many actions, we apply multinomial logistic regression in our work. This regression is just output the probability of each label and choose the max one. To be more specific, it uses maximum likelihood estimation to minimize the difference between predicted and actual label.
Now we are going to introduce the main approaches of our algorithms. First, here is our main approach. First method. In this method, we build 3 streams: human stream, object stream, and pair stream. The pair stream means that we pair the human and object in the image. And for human stream and object stream, we use AlexNet as the fundamental structure. In the image below, this is the architecture of AlexNet. And for a pair stream, we build another convolutional neural network. When training, the input of human model is the cropped human image. The input of object stream model is the cropped object image. And for the pair stream, it is the union region of human and object. After forwarding the inputs through the models, we can obtain 3 vectors, and we perform an element-wise sum of the 3 vectors. After that, we can make predictions and decide which action it belongs. Here is the overall workflow of method 1. In one image, we can crop out the human image, object image, and pair image. We pad it with zeros and resize the size of each image to 128 by 128. And after going through human, object, and pair models, we can obtain 3 classifications. And we merge them by summing up the 3 vectors, and we have 1 output scores.
As for method 2, this is our workflow. First, we crop the original image into 4 images: agent, object, union, and intersection. Then we use AlexNet to extract the features. Our AlexNet is activated from FC7 layer, which is the second layer of a 4-connected layer. And then we concatenate these features and apply classifier. Here we use multinomial logistic regression, and the final output is just action. We implement extraction in extractFeature.py. The input is the set of 4 images. It extracts the feature using AlexNet, concatenate them, and then output is the big feature. As for training, we use the method in the dataset improvement to split dataset. Extract feature using extractFeature.py. Set features, train a multinomial logistic regression to predict the action. And in test section, we use the test dataset splitted by function train test. Then load features and classify. In the end, test the accuracy and draw the confusion matrix.
Now let's talk about the results and analysis. We have 4 types of experiment. Experiment 1, we want to compare the performance between the 2 methods. In experiment 2, we want to improve the dataset and train to see if the results gets better. In experiment 3, we want to train method 2 with the transfer weights from method 1. In experiment 4, we want to add additional classifiers to help classify the labels. So here, the table shows the overall performance and compare method 1 to method 2. And we will analyze detailedly in the following slides. Now let's look at experiment 1. In experiment 1, the models can already predict precisely on certain labels. However, labels like hold, jump, look are easy to be misclassified. After observing the dataset, we found that there are dependencies between the labels, like the actions skateboard is all included in the action jump. The action ride is included in the action sit. We want to remove the dependencies between the labels. So here we have experiment 2. We modify the dataset to avoid label dependencies so that the model will not be confused by those actions. And the results is pretty good. Those labels that were confused now nicely predicted, and the accuracy greatly increases on both method 1 and method 2. And we can see that method 1 still slightly outperforms method 2. So we're thinking that the reason behind it is because the method 2 uses AlexNet default parameters. However, the parameters distribution might not correspond to the distribution of our own dataset. Therefore, we want to introduce the transfer weights from method 1 since those weights are fine-tuned by our own datasets. So in experiment 3, we train method 2 with the weights trained by method 1, and the accuracy also increases, and this also proves our idea. In experiment 4, we want to train additional classifiers to classify some labels that are easy to confuse, such as ride and sit, skateboard and snowboard, catch and throw. However, the performance did not go well as expected. We suppose that is because the classifiers trained by method 2 is not applicable. And in method 1, the model structure is changed and there are more misclassifications beyond what the classifiers can solve. So let's wrap it up. In experiment 1, both methods performed poorly, and we found that there are label dependencies in the dataset. After modifying the dataset in experiment 2, the accuracy of both methods increased. And in experiment 3, we utilized the trained weights in method 1 to perform logistic regression, which is method 2. And the accuracy also increases. In experiment 4, we wanted to use additional classifiers to classify similar actions, and the performance increase is limited.
Now we are going to tell about our limitation of our works. Bounding box are necessary for our models to perform further recognitions, and our models can only apply pictures contain one person and one object. Therefore, it can only recognize one action per image, and Alex might be too simple for our function and not able to extract enough useful features. Now we are talking about our practical use. And first, we only obtain the agent, object, union, and intersection pictures, and put it in specific folder. And we input the action and picture ID, and the code will load the single image and extra features, and it will load the models we choose. The model can predict the action categories and show all the imagery. Here's some example. First, we input the action seat, and we input the image ID 001, and it will show the pictures and show the action it predicts.
Now, we are going to conclude our project. In our project, there is still lots of room for improvement. In the future prospect, we want to use YOLO to recognize human and object respectively instead of throwing the bounding box. Secondly, we want to establish pairwise connections between human and multiple objects and corresponding union regions as input. In this way, our project will not be limited to single object. Lastly, we hope to replace with deeper networks to enhance generalizability. As for experiment conclusion, we have learned that data observation and preprocessing is really important. Although it is the tedious part, it still plays the crucial role deciding the result of all the projects. Secondly, based on our experiments, we can learn that deep neural networks combined with logistic regression can obtain the best result on the task. Okay, and this is the contribution of our member and the GitHub link. and this is our reference. Thanks for your listening.